Okay, so you remember the massive DeepSeek moment back in January 2025, right? The expectations for them have been absolutely sky high ever since. So, why is their next big release just a technical paper? Well, today we're diving into exactly that. It's called MHC, or Manifold Constrained Hyperconnections, and this paper might just change the entire AI game.
I mean, we all remember that moment. Their R1 model went toe-to-toe with OpenAI's O1, and it didn't just keep up. In some cases, it was even better. And it did all that at a fraction of the training cost. It totally reset the bar and got everyone asking, okay, what are these guys going to do next?
Which brings us back to the big question. With all that incredible momentum, why release a dense academic paper instead of a shiny new model? That's what we're going to unpack today. We're going to trace what MHC actually is, why it even needs to exist, and what it tells us about where the AI race is headed in 2026.
To really get what DeepSeek is up to, we have to rewind a bit and talk about this weird problem that's been nagging at AI for years. It's the paradox of scaling. You see, the industry's default instinct has always been, just make it bigger. More data, more compute, more layers, more everything.
But here's where it gets kinda strange. Let's say you have a 20-layer neural network and it's doing a great job. Logically, you'd think, hey, let's make it a 56-layer network and it'll be a genius. But what happened in reality was often the exact opposite. The deeper model actually got dumber. Its performance got worse. So the billion-dollar question is, why?
Well, the culprit is a nasty little problem called vanishing or exploding gradients. Basically, for a model to learn, it has to send correction signals backward through all its layers. But in a really deep network, that signal can either just fizzle out into nothingness, that's the vanishing part, or it can spiral out of control, just amplifying into pure chaos. Either way, the model completely loses its ability to learn.
And this is the perfect way to think about it. Imagine a game of telephone, but instead of a phrase, you're passing along a simple drawing of a cat. Each person redraws it based on the version they saw. By the time it gets to the end of the line, the nose might be gone, the whiskers might be gigantic. The final image is this distorted mess. The essential catness is just lost. That's exactly what's happening to information inside these super deep networks.
So you can imagine the industry has been trying to fix this for years. It's all about fixing the plumbing, the fundamental way that information flows through the network. And there have been a few big attempts to solve this paradox. So the first huge breakthrough came way back in 2015 with something called ResNet. The idea was pure genius. They created a sort of express lane, a bypass that let the original, clean input skip a few layers and get added back in later. This stabilized the whole system, and honestly, it became the gold standard for almost a decade. But then, the transformer architecture came along and threw a whole new wrench into the works.
See, when developers tried to apply these old fixes to the new world of large language models, they ran into this really frustrating dilemma. It all centered around something called layer normalization, or layer norm for short, and depending on where you put it, you were forced into a really tough trade-off.
It was like this frustrating seesaw. On one side, you had the original method, called post-LN. But that brought back those pesky vanishing gradients, which made training a nightmare. So, starting with GPT-2, everyone flipped to the other side, pre-LN. And that fixed the stability, sure, but it created a whole new problem called representation collapse. The deeper parts of the model all started to think the same way, which put a hard ceiling on how smart the model could get. You basically had to choose your poison, unstable training or limited intelligence.
So, for a while, that's just where things were, stuck. But then, the story takes a really interesting turn. In late 2024, another Chinese lab, ByteDance, stepped up with a pretty radical idea to finally fix the plumbing for good.
They called it hyperconnections. Their idea was, hey, instead of one big pipe for all the information, what if we split it up? They segmented the input into multiple smaller vectors, creating all these different streams for information to flow through. The hope was to get the best of both worlds, no more vanishing gradients, and no more representation collapse.
And when you looked at the results, I mean, wow, it looked like they'd cracked it. The models learned almost twice as fast, they developed much richer ways of understanding information, and their reasoning got better. It really seemed like they'd solved that whole seesaw problem. But there was a huge, hidden catch.
The whole system was chaotic. It worked just fine in smaller networks, but as you started to go deeper, the signal could just amplify out of control. By the time you hit the 60th layer, that signal could spike by more than 3,000 times. It made the model completely unstable,
and totally useless for the kind of massive scale the whole industry was aiming for.
And that is the exact problem DeepSeek decided to tackle. They looked at ByteDance's chaotic but promising idea and thought, okay, we can fix this. They came up with a truly elegant solution to tame all that chaos. So their method, this MHC thing, it keeps the awesome multi-stream design of hyperconnections, but it gets rid of the chaos. They start with that unstable architecture, but then they apply this incredibly clever bit of math called the Sinkhorn-Knopp algorithm. You can kind of think of it like a mathematical organizer. It takes those wild, chaotic connection matrices and gently forces them into a very specific, very constrained geometric shape. And the result? A predictable, stable, and well-behaved flow of information.
The secret sauce here is the structure it creates. It's called a doubly stochastic matrix. Now, that sounds complicated, but the idea is actually pretty neat. It's a special grid of numbers where, first, every single row has to add up to exactly 1. But here's the magic part. Every single column also has to add up to exactly 1. This super strict rule makes it impossible for the signal to ever explode or vanish. It creates perfect predictability, which lets you pack in more information and get better reasoning, all without the chaos.
Okay, so let's zoom out. What does all this deep technical stuff actually mean for the bigger picture? Well, it points to a really fascinating split that's happening in global AI strategy right now.
On one hand, you have the US approach, which has pretty much been all in on the scaling law. The philosophy is to just brute force intelligence with bigger and bigger models and absolutely massive amounts of computer power. But on the other hand, you have labs in China who, because they're often constrained on chips and data, are being forced to get more creative. They're focusing on innovating the architecture itself, finding smarter ways to do more with less.
And that's exactly why this paper from DeepSeek is such a big deal. MHC isn't the end product, right? It's a stepping stone. It's the foundational blueprint that's almost certainly going to power their next big flagship model. So naturally, all eyes are now on mid-February 2026, which is when we expect to see the DeepSeek V4 model, built on all these clever new principles.
And that just leaves us with one last really big thought. For the last few years, the AI race has been all about who can build the biggest thing. But what if that's about to change? What if the future of this race isn't just about raw scale, but about who can design the most elegant, the most efficient architecture? That's the huge question DeepSeek's work